Hello everyone, welcome to my presentation for the Artificial Intelligence Planning course in Coursera. The topic of this presentation is how artificial intelligence planning helps get more science on space missions. But first, let me introduce myself. My name is Manuel Fernandez. I got my master's degree in computer science from the Polytechnic University of Madrid in 1998. Then I worked on mission control systems for satellites for nearly 13 years, both for commercial satellites and also on ESA's mission control systems. Then in 2011, I started working on the Rosetta Science Ground segment. In these first slides, I will introduce you to the topic of science planning. There are different types of missions: Earth observation, spacecraft orbiting around the Earth, space observation where the spacecraft orbits around Earth but also fixes on other spots, and planetary missions moving across the solar system. Each spacecraft has instruments to perform observations. Each instrument is used by an instrument team. Observations have lots of different needs. They are placed in different parts of the spacecraft, which means that we have to rotate the spacecraft to use another instrument. Each observation has to meet some geometric and attitude conditions, and there are different pointings required. There are also some incompatibilities between instruments. And then there are other elements to factor in: power, batteries and solar arrays, available memory to store the observations, when to download those observations and free the available memory, and some spacecraft safety constraints plus other conditions. The main objective of the Rosetta mission is Comet 67P, also known as Churyumov-Gerasimenko. On the right-hand side you can see some views of 67P. As for the spacecraft at the top, that's Rosetta. Rosetta is a robotic spacecraft which consists of two parts: the spacecraft itself and the lander Philae. Rosetta has 12 instruments and Philae another 10. Rosetta was launched in 2004 and will wake up from hibernation on the 20th of January 2014. Since it was launched in 2004, Rosetta has gone through a long and complicated way until it meets with 67P, as you can see on the picture on the left. Then on the right, an artistic representation of the lander Philae getting away from Rosetta and preparing for landing can be seen. So summing up, ESA's Rosetta mission is about going to a comet far, far away, landing on it, taking pictures, taking samples. So what is this? Is this Armageddon? And then, where's Bruce Willis? Well, this is certainly not Armageddon. Now let's go and see what happens after wake up. After wake up, we need to schedule all the instruments on board, and each one depends on a different team, and they have to agree on a plan of observations. And some observations combine Rosetta and Philae parts of the same experiments. One of the most interesting parts is comet wake up, when it gets closer to the Sun, but that also causes some instability or simply unpredictable conditions. Yet we still want to use our instruments to make observations and take measurements. The problem described so far is pretty complex, so how do we make it manageable? First, we split the lifetime into smaller segments: long, medium and short-term plans. An LTP takes 16 weeks, containing 4 MTPs. An MTP takes 4 weeks, containing 4 STPs. To handle the unpredictability of the environment, we provide 3 skeleton plans for 3 levels of activity: low, medium and high, and each one of them defines a trajectory. Depending on the observed level of activity on the comet, we will choose a plan and its trajectory. Then we automate the planning. First, we collect instrument teams' inputs as observations. Observations are like templates which have to be fully defined using additional information like the trajectory. But there are other elements to take into account for the planning, such as downlink windows to send the observation data to Earth and navigation support. To include these elements into the planning process, we make them into observations. And finally, we assign observations to planning cycles, LTP and NTP, by defining campaigns that link them together. This way, observations can be reused for other planning cycles by assigning them to different campaigns. The planning problem is still too big, so we have to help by reducing the search space. We do this by identifying periods of time where observations are feasible. Feasibility includes geometry checks, attitude checks, spacecraft constraints checks. These periods of time are known as windows of opportunity. Another way to help is to provide complex resource usage as external functions to the scheduler, but the scheduler does not really need to know all the internal details of an instrument or observation. Contiguous observations might not always be possible, so we provide another helping function to the scheduler. And to maximize science, sometimes several observations might occur simultaneously. This compatibility is also provided as another function to help the scheduler. The final step is the scheduler itself. So we feed the windows of opportunity to the scheduler and provide the helper functions to the planner, plus some additional general data such as instrument modes, power and memory usage, and incompatibilities that need to be checked as a plan is created. And finally, we add some very specific needs, combining contributing observations, accumulated time, and optimizations. This is a simplified view of the Rosetta Science Planning and Scheduling subsystem. All the components in this diagram make use of a database which has been populated previously by users through a web tool. And other external interactions are not shown, as the focus is on the planning process. At the top, the planning cycle is initiated by providing a planning period with a start and an end time. Then, the campaigns covering that period are identified and the observations within each campaign. Those observations are expanded with conditions from the campaigns before going through window identification. The window identification component creates windows of opportunities, WOOs, per observation by checking its feasibility as far as geometrical and attitude conditions are required. The scheduler input preparation collects the windows of opportunities, the observations, and the campaigns for the scheduler. The scheduler uses those inputs to create a schedule by placing observations within the window of opportunity. It also checks if other simultaneous observations are possible using the pointing compatibility helper function, and if the observations can be contiguous using the slew checker helper function. The resource functions provide the usage of resources per instruments during observations to make sure they are within limits. The final steps are the conversion of the plan from the scheduler into the planning products used, a plan of the pointings, and a plan of telecommands required for the observations. The simulator further reviews the plan to generate a resource profile and make sure that instruments do not get into inconsistent states. Aspen is a framework for automated planning by JPL. The scheduler component from the previous slides is a customization of Aspen for Rosetta. The customization includes reading all input data into Aspen using Aspen's modeling language, and it also includes using the helper functions described in previous slides. Aspen has different planning algorithms available that can be exercised on the same planning problem. The main idea is that some planning problems might get better results using one algorithm because of the domain of application. Making the algorithm selectable helps explore which one does better. In this slide you can see the output of the scheduler as a timeline from left to right, with observations as blocks placed on the timeline. At the bottom, the campaigns applied to the planning period are provided. Different plan results from the scheduler are created by changing conditions on observations or campaigns. Comparing different plans with the conditions that generated them helps a lot when making decisions about which plan to use. Here you can find some references about Rosetta, Aspen, and the space planning problem in case you want to know more. Finally, I would like to thank Lawrence O'Rourke from the European Space Agency and Steve Sheehan from the Jet Propulsion Laboratory. Thank you for watching my presentation.